Dr. Depcik is here today from the Mechanical Engineering Department, and it's kind of interesting to see what he will present about with his title up here. But anyway, Dr. Depcik joined KU about 6 years ago after receiving a PhD in Mechanical Engineering and 2 master's degrees. He has a master's in Aerospace Engineering and Mechanical Engineering. His research revolves around sustainable approaches to energy and the transportation infrastructure. And this includes the Feedstock to Tailpipe Initiative, and where he looks at the biofuel production and combustion and analysis of emissions all along the whole spectrum. And Chris mentors many students at KU, and he's the leader of the EcoHawk program. And he's also mentored several of the high school teachers and community college teachers involved in our Research Experiences for Teachers program. And he has received numerous awards, including a Kemper Fellowship in 2011, which was campus-wide recognition of his teaching excellence. And also he received the Society of Automotive Engineers Ralph R. Teeter Award for his transportation-related research and educational activities. So it's my pleasure to introduce you. Thanks for coming to BBC.
Well, thank you all for having me this morning. I decided to have a little bit of fun with the title today. Now that I have tenure, I guess I can do that. The common joke is when I have to explain my research, I got my PhD in catalytic converter modeling. What I was talking a little bit earlier about is when people ask you, what do you do? And if you start talking about catalytic converters, you see the eyes glaze over and you have to go into a lot of description with what's going on. So instead, I just typically say I like to burn stuff, which is true. I do a lot of internal combustion engines testing in addition to the catalytic converter work. So I'm going to give you an overview of kind of all the different activities that are ongoing here at the University of Kansas in the area of combustion and fuels. As mentioned before, a little bit about my background. I actually do have a courtesy assistant professorship in the Department of Chemical and Petroleum Engineering for the catalytic converter work I do. So I have a mechanical engineering background, some aerospace engineering background, and chemical engineering work. So that means I have no idea what I'm doing. I cross all topics. And my research emphasis is a sustainable approach to internal combustion engines, automobiles, and energy infrastructure. So my standard joke is I like to burn things, so I figured the topic talk was Burning Man, so I need to show a burning man. In order to, it's first thing in the morning, everyone got to get a get going. The outline I'll talk about, I'll discuss a little bit about the feedstock to tailpipe approach if you're not familiar with it. My specific area in that, alternative fuel assessment, and then I'll discuss the different types of engine setups that we have. Single-cylinder engine test cell, a multi-cylinder engine test cell that we're getting up and going. I'll talk about our syngas rig, waste heat recovery, in order to look at the co-products through syngas and waste heat, and then exhaust after treatment modeling. One of the students, Travis, that I work with is here, and then I'll summarize the efforts. So the KU feedstock to tailpipe approach is really kind of wholly unique to universities, that we look at the entire system of biofuels. We look from the ecosystem level processes, dealing with ecology, evolutionary biology, and geography, to the biomass production, again, biology, environmental and chemical engineering. So we look at how these fuels impact the land, how we produce these fuels, through the production methodology in terms of, you can see some nice green with respect to algae growth, the biomass pre-processing and chemical transformation. How do we take these raw feedstocks and convert them to a biofuel? And then alternative fuel assessment, which is my area where we look at how these fuels perform in an engine, which is critically important. And you can see the circular nature of this. You've got to grow the fuel. When you got to see how the fuel impacts the land environment as you're growing it. Then you also need to grow the fuel. Then you need to convert to a fuel, and then you need to burn the fuel. But when you burn the fuel, you have CO2 emissions, which end up impacting the ecosystem level process. So it's really a wholly unique infrastructure in terms of analysis. And that's critically important because a lot of the times when you do the analysis, you're looking at a specific portion. And you keep your blinders on with respect to what's downstream and what's upstream. I know when I was at the University of Michigan, if we got a biofuel in the engine laboratory, we really didn't care where it came from. We just saw how it performed in the engine. Did it perform well or did it perform poorly? Well, if it performed well, we said that was a great fuel. But what if it took a lot of land, to produce? What if it took a lot of energy? What if it was hard from a catalytic standpoint, that used a lot of catalytic material? Then maybe it's not the best fuel. So it's important that you have to understand the entire methodology. And that's what we try and do here with the feedstock to tailpipe objectives. We look at the ecosystem level processes. We use models to study the effects of feedstocks on temporal and spatial changes in landscape carbon dynamics. We look at biomass production. We want to maximize the growth using sustainable methods. Belinda Sturm is working with us in that area, and for instance, she uses the wastewater treatment plants in town in order to grow algae. So you've got a feedstock-rich source that would just be a nutrient-rich source that would be effluent to the river otherwise. The biomass pre-processing and chemical transformation. Work with Susan Williams in that area to develop more efficient reactors and catalysts to produce biofuels and also higher value co-products. You can't look at just the biofuel itself. You got to think about the co-products that come along with it. And then alternative fuel assessment. You need to evaluate the combustion and emission characteristics of the biofuels produced. If you don't do that, then you can't sell the fuel. Keep in mind, petroleum industry has had 120 years to develop their fuels. Do you think the first fuels that they developed worked well? No, they didn't. So biofuels have that amazing stigma to overcome in terms of they've got to work right from the first get-go. If they don't, then you hear a lot of bad things about them and people are reticent to use them. So if we look at the issues that biofuels have that we need to consider, well, obviously price is up there. Safety, how safe are they? I think someone said that if you were to develop gasoline today, the EPA and OSHA would never allow it because of how dangerous it is. Think how dangerous gasoline is. You pour a little on the ground, you can light it, bad things happen. Right? Reliability, it's got to work every time. Performance and emissions, how well does it perform in the engine? Now you have to look at the life cycle production of these biofuels, the renewable fuel standard. The second one that came out looks at the whole picture involving these fuels. Energy content, material compatibility. Not a lot of times that's thought of in engines. If it eats through your seals and your O-rings, then all of a sudden you've got issues. So engine companies have got to think about those compatibility issues. And then also infrastructure. For example, I believe the jet fuel, they only allow 5 parts per million of biodiesel in the jet fuel lines because the aircraft industry is really reticent to what biofuels will do in jet fuel. Good example of that, look at the fuel freezing quality. We've got jet aviation. We got 100% biojet that might be from upgraded to be a Fischer-Tropsch process, and then biodiesel at 30 degrees, minus 30 Celsius, basically solid. Do you really want that in your airplane? Yeah, I didn't think so. That's why they only want 5 parts per million of this in this. So you've got to think about all these biofuels issues. Petroleum fuels, like I mentioned, have had over 100 years to develop. Biofuels are, besides ethanol, it's been around since the 70s. All these new biofuels, the upgraded type, the B100 biojets, are really just new. So what I do, what my students do, when we look at developing the right biofuels, this does require engine testing. It cannot be done in a vacuum without engine testing. The physical fuel properties influence engine performance and emissions. Perfect example of that. Here we have the same engine. Here's jet fuel, JP8. Here's ultra-low sulfur diesel. And here's biodiesel. We did not change injection timing at all between those fuels. This is pressure as a function of crank angle, so it's telling us in cylinder when each fuel is combusting. We didn't change anything. We just put the different fuels in. As you can see, that makes a huge difference with respect to these different fuels when combustion is occurring. That impacts fuel economy, that impacts the nitrogen oxide emissions coming out of it, particulate matter emissions, everything happening in the engine. What does the customer want? The customer wants a fuel that drops in that works perfectly, right? It's not going to change their fuel economy, not going to change their emissions. They may not notice that, but the EPA will notice that. But this is not what you see when you create a new fuel. They will always have different characteristics. because they're not petroleum ultra-low sulfur diesel. So the physical fuel properties do definitely influence engine performance and emissions. So you have designer singular fuels or blends for the right characteristics. You've got to look at these fuels and say, can we blend them right? Can we take biodiesel and JP8 and make it a ULSD? You could do that. You can imagine if you just average those, it would be right in the middle. It doesn't exactly work that way, but that's part of the analysis that we try and do. In order to do this right, we need high accuracy and low variability experimental data. We need a good engine test cell where we can look at specific fuel characteristics and how they impact when peak pressure is, the fuel economy, and the emissions that come out of it. And so that's why I was brought here, is to start doing that type of work. So in Learned Hall, I have a single-cylinder engine test cell. And single-cylinder engines are great because if you take a multi-cylinder engine, you've got a lot of variability in there. Each of the cylinders, 4, 6, 8 cylinders, will be operating differently. It's nature. Flow is going to be different. Heat transfer is going to be different. So if you're trying to find how these individual properties impact engine combustion, performance, and emissions, multi-cylinder engines are difficult to use because cylinder 4 might be performing differently than cylinder 6. So single-cylinder engines basically remove all that variability and say we have one cylinder, and we're just going to control that cylinder very finely. We're going to instrument it as much as we can to get everything out of that. So what we did was we took a Yanmar L100 diesel engine as part of a generator. So when I came here, no engine test cell, no students trained in this area, no one with any experience except for myself. My background was PhD in catalytic converter modeling, so I had a little experience, but not in engine test cells. So we took a generator. The generator had this diesel engine, and we tore it apart. Along the way, I was able to get funding in order to add a dynamometer, which is an electric motor that allows us to finely control the load on the engine. We added a FTIR for gaseous exhaust emissions. We added a smoke meter for PM emissions. We actually have a turbocharger on it, which is wholly unique. Typically, you don't find turbochargers for one cylinders. There's actually a snowmobile company, Aerocharger, in 30 minutes away that makes turbochargers for small bore engines. And they just gave us one. So we were very lucky on that aspect. We developed our own cooled exhaust gas recirculation loop, external system. I think that you can see that on here. That allows us to take exhaust gases and bring it into the intake, and that's one methodology that engine companies use to reduce NOx emissions because it's an inert species. We also have a gas-assisted intake system. So CNG is huge nowadays because of the cost. Can we run CNG-assisted biofuel combustion? You bet. So we set up this single-cylinder engine to utilize pretty much any fuel. It's a diesel engine, so they're diesel-type fuels, which are jet aviation fuels, diesel. You could do ethanol-assisted diesel. That's also a possibility. We could add exhaust to it, gas-assisted to it. We've done hydrogen-assisted biodiesel combustion. We've thought of everything in the single-cylinder engine test cell in order to allow us the most flexibility with testing the different types of fuels and whatever gases that come off. And this is all highly regulated from an accuracy standpoint. We have a very low experimental error, and that's needed. So that allows us to really understand the characteristics.
Chris?
Yes?
Is that diesel engine, in other words, for testing fuels, is that the one recommended that would then translate to maybe a transportation vehicle if you have tested it in this and certified the fuel? How did you choose that?
It's a good question. The question is, why did we choose this engine? How did we choose this engine? Would it translate to a vehicle? Not necessarily. We chose this engine because we could get it relatively cheap. It's very robust. Parts are easy to find, and it allowed us to have the most modification. If we wanted to go towards a realistic vehicle operation, we need a multi-cylinder engine. This is great for fundamental studies, so that it allows you to design better characteristics of fuels. Some of that information will translate over, but we do need a multi-cylinder engine test cell. And we do have one. And you'll see that in a minute. Another thing that's wholly unique to our engine is that it came with an older style injection system. That may not mean anything to you, but to me it means a lot. We need to have it reproduce as much as possible a production engine. So we actually tore off the injection system and added a high-pressure rail injection system. Bosch, ECU, and a fuel pump you find in the 2013 Jetta. Same type of system. We actually have a Fiat Punto injector from Italy that happened to be just the right size to fit in our engine. One of the most serendipitous, lucky things we've ever found. But it allows us to dynamically control fuel injection to the point we can inject up to 5 times per one thermodynamic cycle. So we can change our injection event to have 5 different injection events for one thermodynamic cycle. So think about how much time you have for one combustion cycle, and now imagine being able to inject 5 times different amounts of fuels. So we dynamically control fuel quantity, fuel rail pressure, 40 to 200 megapascals. Fuel pressure, 200 megapascals. This is where the industry is going. Finer and finer atomization through higher fuel pressures. And we can do this to 0.02 crank angle resolution. Why is that critically important? Let me go back to the previous slide. What do we want to do with these fuels? If we do testing and leave ignition timing where it is, we're missing some of the properties of the fuel and how that impacts combustion because it's not normalized, right? Combustion is not happening at the same time. So you have higher temperatures, different pressures. You cannot see exactly what's happening. So by going to this high pressure system, and I'm going to walk over here for a second, this is what it looks like if we just let the fuel burn. And we've got palm, Jatropha, soybean, beef tallow. These are all biodiesels, 100% biodiesel. Here's our ULSD, our diesel. You can see that if we just put the fuel in, our combustion timing changed. We're losing some of the impact of properties because that's being overwhelmed by the influence of the change in combustion timing. By adjusting our combustion timing so that our peak pressure occurs at the same point, now we get a better understanding of how the fuel properties influence combustion. We can see right there and there the energy content of these fuels is less, so we're not going to have high peak pressure. We start getting a really better understanding of combustion and the impact of fuel properties. And this is a perfect instance of this. Here's Pearson correlation coefficient showing stronger trends after normalization, after we've adjusted the injection timing for NOx. We see our cetane number, we see a much stronger correlation from the unadjusted to the adjusted to the normalized. Same thing with the degree of unsaturation. Same thing with unsaturation percentage of polyunsaturation. By adjusting the injection timing so we normalize these fuels from a combustion standpoint, we get a really good understanding of how the properties are actually impacting things like NOx. What does that mean to us? That means then I can go to my colleagues in chemical engineering and say, you want to have a little bit more of this or a little less of this, because then we can start tailoring the fuels to have less NOx production, carbon monoxide, better fuel economy. You name it. We can design a fuel that works better. How would that happen without an engine test cell? And without the proper characterization and normalization? You wouldn't be able to have that. You would just guess and say, this looks good. Maybe it's easy to produce. Maybe it's cheap. Great. But if it doesn't perform well, then that doesn't work well in the overall industry. So that's an upgrade that is critical. And you can see in some of these where we didn't have a strong correlation before, we had a weak correlation, now it becomes strong. Now we can say for certainty, this is what happens. And this is an example illustration. This is the paper that we created for energy and fuels before we upgraded the injection system. And now we're doing a follow-up paper where we can look at these characteristics such as the hydrogen-carbon molar ratio and how that impacts things like NO, NO2, total hydrocarbons, particulate matter, brake-specific fuel economy, which is fuel consumption. And we can create a table so that we can go back and say, maybe you need a little bit less viscosity. Maybe you need a little more viscosity, depending on what you want to do. And we can start, for some of these relationships that we weren't able to determine before, we can start figuring out those relationships so that we can develop these better fuels. That's what the single-cylinder engine is great for. Really fundamental, what is happening, how is that a function of the fuel properties? This also allows us to test things beyond biodiesel. You've got an interesting fuel, you've got an interesting concept, you want to do it maybe for the military. The military is jumping beyond your first generation biodiesel, diesel, to the next generation diesel. And the reason they want to do that is because they want something that's just drop-in, that works perfectly. They don't have to worry about the fuel gelling. They don't have to worry about any degradation in storage. Another thing is, the military likes the single fuel forward policy, which means that they want to simplify the logistics in moving fuels. You've got gasoline vehicles, you've got diesel vehicles, and you've got jet airplanes. You've got to transport 3 fuels, right? Imagine each fuel costing $500 a gallon. It's not like they're growing it in Afghanistan. They've got to transport it in themselves. So they've moved to a single fuel forward policy, which is pretty much JP8. They also want to drop in fuel. They want to go straight to green diesel. So what this allows us to do, our engine test cell, is we can actually test green diesel. And here you see ULSD with the JP8, the conventional petroleum JP8, and we were able to get Centrolian R8, renewable jet fuel 8. And we were able to show its different characteristics. While that may look worse, because you're able to tailor a green fuel, they actually found improved fuel economy. Well, I should say we actually found improved fuel economy with lower NOx, carbon monoxide, and hydrocarbon emissions. And over the entire realm, we actually found reduced particulate matter emissions. Those are a little bit higher, but most are lower. So this indicates that if you can create a synthetic fuel, drop in green diesel, and you know how to tailor it, look at that market that opens up for you. Better fuel economy, better emissions. Do you think the Army would be interested in that? I would say yes. Very much so. So, the idea behind it is not to just burn things, like I said I like to do, but also understand what happens when you burn things, and then feed that downstream and feed that upstream to create these better fuels. However, single-cylinder engine test cells do have their own limitations. You can develop a great fuel in a single-cylinder engine test cell. You can publish a lot of information on it, but the industry is really not going to believe you until you test it into a production engine. And so we have a new multi-cylinder engine test cell that's opened up in M2Sec. We have a 351 horsepower AC dynamometer here, which has got 1,000 newton meters of torque, which if you don't know what that means, it's a lot of torque. It can handle a lot. We have a production engine, a 6.6 liter V8 GM Duramax diesel, and we're setting this up so that if we do develop a really good fuel, we can test that in this production engine, and that way we have our final justification. Another thing is, we have this big dynamometer. This engine will probably take 6 months to about a year to set up properly. Do you think I'm going to take a new graduate student or an undergraduate student and put them in that lab and say, have fun? Combustion, highly dangerous, things spinning very fast. Not a good situation. This AC dynamometer is the big brother of the AC dynamometer that we have in the single-cylinder engine test cell. The single-cylinder engine test cell is 12 horsepower. This is 351 horsepower. So what this allows me to do is take new graduate students, put them in the single-cylinder engine test cell, say, learn here. Get your master's degree on this. You want to stay for your PhD? Oh, you get to go to Big Bertha and have fun. Right? Isn't that a great way of training students so that they prove their expertise on the single-cylinder? If they destroy the single-cylinder engine, I can go pick up another generator, pull the engine out, put it in. We're out maybe a month or two. They destroy this engine, oh, we're in trouble. We're in a lot of trouble. So you have to think about training students along the same time. This isn't a small reactor. This is something burning under a lot of pressure, with a lot of heat, and a lot of power. They've got to be trained well. So I have 2 PhD students right now that are working on getting this going. Finding funding for it is always a challenge. It's the chicken and the egg, right? You need to have the engine to get funding, but you need the funding to build up the engine test cell. So we're working on that. So that is where we're going with engine testing. Our single-cylinder engine is going to just keep chugging along for forever. We're happy to throw any fuels in there that you want. We've put in, jet fuels. We put in something else. Say, you name it, we probably put it in there. If you want to try some ethanol-assisted diesel, biodiesel, jet fuel, great. We're all game for that. We love burning things in our single-cylinder. But another thing that's critically important when you look at biofuels is the byproducts. There's a lot you can do with the different byproducts. But because of my background, I like to burn things. So when I look at the byproduct for things like biodiesel, I look at glycerin. 1 gallon of biodiesel creates about 1 pound of glycerin. If you look at the economics of biodiesel production, it's really tied to glycerin. At times, you've seen glycerin as low as about 5 cents per pound. If you take into account the density and the energy basis, this is about $1.11 per gallon for glycerin. Glycerin's great. Glycerin's got a lot of hydrogen. It's a great hydrogen carrier, right? What could you do with that hydrogen? There's a lot of higher value products that you can get. Pure glycerin is great from a selling standpoint, food standpoint, but if I've got a hydrogen-rich fuel, and if we look at the amount of this hydrogen-rich fuel, and it's going to keep increasing as a renewable fuel standard sees more diesel on the market, I want to do something with that from an energy standpoint, especially when I start looking at $1.11 per gallon. So what you could do, could you use it directly as a fuel? Well, it's subject to caking or settling and solidifying the fuel lines. So no. Could you use it as that fuel additive? And people have done that if you look at the SAE literature. The atomization difficulties due to high viscosity results in poor emissions and low combustion efficiencies. So no, it does not work well as a fuel additive. What could you do? You can convert it to a synthetic gas, syngas. You can look at the glycerin, you can do some partial oxidation, you can do some water gas shift reacting on it, steam reforming. You can pull off that hydrogen, you can pull off the carbon monoxide. If you can do it right, you get a lot of hydrogen and some carbon monoxide. As an engine tester, do I care about carbon monoxide? No, it's a fuel. It's got an energy content, 10 megajoules per kilogram. You give me an engine, I can run it on carbon monoxide. It's a fuel. It can be used. And I did that, actually. I should say we did that. Here is, I mentioned the gas-assisted system, our single-cylinder. We took a hydrogen carbon monoxide mixture. We put it in the intake of our diesel engine, and we were able to run biodiesel and find that we could reduce the biodiesel fuel flow rate below diesel when assisting it with hydrogen and carbon monoxide. So we could get better fuel economy of biodiesel by using syngas in the intake. So imagine if you had a biodiesel production facility. You take the biodiesel, you go to a diesel generator, take the glycerin, create a syngas, and send that syngas to the generator. So you're assisting your generator with the syngas while also burning biodiesel in order to run your biodiesel production facility. Renewable fuel credits, everybody's happy. Your fuel's right on site. You don't have to transport the fuel. A lot of logistics there. Perhaps more exciting is what we're doing here, a direct pathway to power in one continuous process. I think we're the only institution in the United States that can do this. And I'll show this in a second. We take glycerin, we convert it to a hydrogen-rich syngas, and we send it directly to an engine, and we burn it. Why? Because we can. A lot of things I do is because we can, see if it works. We have a one-of-a-kind equipment setup. We can run the engine on pure propane. So we have a fuel reformer, a Chevy V8 350, and a three-phase electric generator, all in one continuous flow process. We can run this engine on pure propane. We can send propane to the fuel reformer to warm up the reformer to get it ready for the catalytic conversion of glycerin. Then we can run this engine off the syngas that's created from reformed propane. Or, once the reformer's hot, we can take glycerin, we can convert it in the reformer, send it right to the Chevy 350. Great power. One continuous process. I think we're the only institution that has this type of setup in the United States, where you do it in one continuous process. I spoke 2 months ago at a National Advanced Biofuels Conference. A lot of people there, biodiesel industry, they said, this is fantastic, this is great, and so hopefully we'll see something come of this. we look at the flow chart of the engine, we have a propane tank. We can regulate our propane. We can send it to the Chevy 350 and create power. Our air comes in through a different line. Then we can take this propane. We can send in compressed air into our reformer. The reformer will heat up as we're basically doing rich combustion in the reformer. Our syngas comes out. It's cooled down, sent to the engine, and we can run the engine. Once the reformer is nice and hot, then we basically put our glycerin in. We use a 20% water, 80% glycerin mixture in order to promote the water-gas shift reaction, in order to get more hydrogen coming out of it. Goes into our heat exchanger, cools our syngas, power. All instrumented. We have in-cylinder pressure transducers. We can actually measure the entire process.
Chris, when you do this is really very intriguing. When you do the overall energy balance, does the heat required for the reformer self-sufficient?
Yes, we actually had to take out some catalytic material because it was highly exothermic. When we start putting the glycerin water mixture in here and we get this nice and hot, it maintains itself extremely well, to the point that we have to really watch it because otherwise it'll take off. And so we've used glycerin conversion over nickel. So we tried to do the literature research and had help from Susan Williams in this area. 7.2% weight percent over alumina oxide support. We just bought alumina oxide beads. My graduate student in mechanical engineering actually did the weight percentage coating himself with an oven. So I do a little bit of chemical. I don't pretend to understand what's going on, but I know how to get to 7.2%. I should say my students do. It's highly exothermic. So we could probably reduce the catalytic weight percent. We probably could put less material in there. We have not optimized the system. We're very much in the proof stage. We tested at 3.6, and 6.5 kilowatt generator output. And this is actually the model, basically simple chemical equilibrium model that my student created. And these dotted lines, these dots here were basically his model prediction, capable of operating at no load. Triangles capable of operating at one load, which is the 3.6 kilowatts, and the squares were capable of operating at two loads, 6.5. The circles here indicate our tests with flow rates for the glycerin and the airflow rate in order to achieve repeatable combustion and just have it go steady state. You can see a lot of room for expansion. There's a lot of potential here because we have a lot of glycerin that we could increase the flow rate of both the air and the glycerin. A lot of potential power. So we have significant potential for expansion. We're busy writing up this work to get it published, but it gives you an illustration of where we could go. You can also convert the syngas to other fuels. So imagine if you had this huge glycerin tank. Create your syngas. You could send that to power. You could also send it in other directions. You could use it to create methanol that could be used in the biodiesel production process. You could create ammonia. You could upgrade it to renewable jet fuel. There's that potential to break it off in different processes. So there's significant potential. So we're looking at just one co-product. So if you look at it, from one feedstock source, we've created two biofuels. We could use biodiesel or glycerin. And that's wholly unique, I believe, to KU. Another option is, I hate to admit it, internal combustion engines are really not that efficient. Don't quote me on that because I will deny it in the grand scheme of things, but they're not that efficient. They create a lot of heat. You felt it, right? You walk outside, you drive in the garage, you can feel the heat radiating from your car. In reality, you're about 25, 35% efficient, maybe a little bit higher. The rest of the energy goes to the exhaust and coolant. So why not integrate heat exchangers? Why not put a heat exchanger in your coolant system? Why not put a heat exchanger on your exhaust? What could you do with those heat exchangers? What could you do with that energy? Well, how about using that energy to heat your oil for the biodiesel production process? Or using your energy to remove glycerin through basically you need to distill the product coming off that glycerin in order to get a more pure form to be better suited for catalytic conversion. So there's a lot of energy that can be useful for oil processing, glycerin distillation. You can also use it for secondary thermodynamic cycles for additional power. I'll get to that in a second. So this is what we're busy doing now. We're moving the system to a new area on campus, and we're looking how to integrate heat exchangers to get an even better energy balance. This one I like, secondary thermodynamic cycles for additional power. You got heat, you got energy, let's convert it to electrical energy. And that, I have a student working in this area and he's doing his PhD on looking at waste heat recovery. If you take organic ranking cycles for exhaust energy recovery, it demonstrates potential 10% improvement in fuel economy. 10%. You know what the industry is trying to do each day? Is get a fraction of a percent better in fuel economy. 10%. It's been used in the past. In the 70s, when we had the oil crisis, they started looking into these secondary thermodynamic cycles. It will be used in the future. The cost benefit is attractive. You can pay for the system in a couple of years on board a vehicle. If you don't believe me, my student wrote a review paper in the subject, and I'd be happy to send it to you. It's actually the #1 most downloaded mechanical engineering article in 2013 from Elsevier. To show you that this is really where the industry is going. We're implementing this in a single-cylinder laboratory as a precursor to multi-cylinder efforts, and we have a novel idea here. The novel idea is, for direct injection engines, they produce a lot of particulate matter. Particulate matter is captured in a filter in the exhaust in your new diesel engines today, diesel particulate filter. You've got to regenerate that after a while because you know your vacuum cleaner, right? It's basically a diesel particulate filter. What's a particulate filter? I shouldn't say diesel, but it's a particulate filter. What do you have to do every once in a while with your vacuum cleaner? Empty it, right? Clean it out. Unless you have a Dyson, but we don't have Dysons in our exhaust. So we have to regenerate the diesel particulate that's been captured in this filter. It's carbon. What happens when you burn carbon? When you regenerate it? What do you get? Energy. You get heat. So what if we take a diesel particulate filter, which are these pores here, that traps particulate matter, and let's integrate it in a heat exchanger, and then use that for waste heat recovery. So instead of just having a filter that captures particulate matter and burns it, now when you burn it, we take that energy that's coming off the particulate matter that's being burned and send that to a secondary thermodynamic cycle to create more energy. So think about the entire system here. So we actually have just completed our efforts in this, and we found that we get better heat transfer to the working fluid when we have our diesel particulate filter cores in here, illustrating that we can recover more energy when we integrate a diesel particulate filter into the heat exchanger. So I'm not done. As I mentioned, my PhD was in catalytic converter modeling, and so we had some ideas in the past, and Travis is working on them, is that when we analyze feedstock through the tailpipe, we have to understand the catalytic conversion part. Part of that is waste heat recovery, part of that is particulate matter capturing, but also part of that is how these biofuels will impact the species coming out and how those species change and how catalytic converters have to account for those species change. So we see actually, this is Travis's setup. I probably should reference Travis below. But we have a quartz tube packed bed reaction chamber, a resistive heating furnace, and we're looking at NO oxidation in that in order to look at how these species change, not only from the biofuels production standpoint in the tailpipe, but also how we can convert these species better using less materials. So Travis is working, if you have any questions about this, he'll be able to answer it better. I'm glad he's here today. I'm going to put him on the spot. Look at how the reaction mechanisms change as a function of the particulate matter, the particle size on the surface. So if you can get by with less platinum, palladium, or rhodium on the surface and achieve the same reactivity and build that into the models, we can have cheaper and more efficient catalytic converters. I am the modeling component of that. I've developed simplified models for different fluid dynamic solvents. We can do dynamically incompressible, we can do compressible flow, fundamental adaptive chemical reactions, expressions generated. So I do a lot of the modeling effort. Travis does the actual work. So I just have to sit behind my desk and send something. But The idea is to look at, through the tailpipe here, how these conversions are going to change as a function of different NOx emissions NOx levels coming out. I do have a compressible 1+1D model of flow through a diesel particulate filter. We're basically creating a new model to incorporate waste heat recovery along with that, so that we can see how the flow in the chambers and the heat transfer to your working fluid can be modeled, so that we can do more predictive studies, so that tell us what tests we can do in the future. We're looking long-term to go to engine control unit type of systems. Imagine if you got a more efficient catalyst and you've got a more efficient combined diesel particulate filter heat exchanger, and you have an engine control unit that has simplified models in there that can help control engine operation to get better fuel economy and lower emissions. This is the area that we're working into, including flow-through porous membrane, you name it. We have a lot of capabilities in that area. So basically, the end of the story is, you give me a fuel, built the methodology to test all the way up through what's coming out of the tailpipe. Not only from a combustion standpoint, but from a co-product standpoint, and from a waste heat recovery, from a catalytic converter, and from a diesel particulate filter standpoint. We have all that capability here at the University of Kansas. So biofuels really require the assessment of combustion emissions. We have a single-cylinder laboratory, which is great for fundamental property investigation. The multi-cylinder engine laboratory is under construction. The byproducts, glycerin and heat. Heat is often neglected as a byproduct. We need to include that as being studied. And we have a complete pathway through the catalytic conversion. We're analyzing every aspect of that. I'd like to acknowledge the partners that we've had. Some of these through my colleagues, some of these through myself, NASA, Department of Energy, NSF, City of Lawrence, Department of Transportation, Kansas EPSCoR, KU Transportation Research Institute, KU School of Engineering, and the Kansas Soybean Commission. So I'd like to thank you for your attention, and I'd be happy to answer any questions you have.
Yeah, I really like the idea of that you described of utilizing glycerol as actually an energy source. And if I think about it, the chart that you showed that had all of the different components on, in fact, you just flattened it. Right?
This one?
Yes, and it has all these different components.
Yes.
It looks to me like even though all of these things are well thought out, they would take up a lot of space.
Would take up a lot of space.
And so I wonder if motor vehicles have enough room in them for all of this stuff.
In terms of a motor vehicle standpoint, no. There would be not enough room to integrate a glycerin air system and reformer and go directly to your engine. They actually tried that a number of years past when I was at Michigan and worked with Levi Thompson on a small-scale, it was hydrocarbon to hydrogen fuel reformer. And it just is very difficult to control, and to get it to that miniature scale, it just does not work well. So this is definitely not suited for onboard a vehicle. However, if you're at a biodiesel production facility, or if you're at a biofuels production facility, instead of drawing from the grid, and you've got a lot of glycerin hanging around, you could basically just integrate it there and to create power. And you might say, well, electricity is cheaper. Why won't you just use electricity to create the power? And I agree with you. But being at the biofuels conference, they talked a lot about renewable fuel credits. And that's what the industry is moving towards. They really want a lot of renewable fuel credits. So if they can make their process more exciting from a renewable fuel credit standpoint by using the byproduct, and the EPA likes that, then it helps them sell their fuels for cheaper. And they can basically sell those renewable fuel credits to other producers who need them. So onboard a vehicle, theoretically, yes. Practically, no. But in a steady state system, we have all this in a shed, a small shed, and it works.
Yes. So I have a couple of questions. One related to this. So you are using partial oxidation to produce the syngas.
Yes.
You have glycerol. And so when you do that, often the challenge is how do you curb the total oxidation pathway. So I wonder, you point out that you're getting syngas. Are you not getting any CO2 at all?
We are getting some CO2. We are definitely getting some CO2. We are definitely getting some water. The key is with engines, I talked about exhaust gas recirculation. CO2 and water entering an engine does not influence it at all. In fact, it helps because it reduces NOx emissions, because it acts as an inert. So we just have to keep the CO2 and H2O, obviously we want it as low as possible. But anything that we send to an engine, we just basically use it as exhaust gas recirculation.
The other thing is, with all the nice infrastructure that you're putting together, are those when we talk about things that you mentioned about fuel certification for transportation, they've got a rigid set of standards or protocols they have to go through. I guess ASTM has a methodology. So would these be like what you're close to ASTM certification, or how do you characterize that? Because ultimately it has to go through those expensive protocols, right?
Exactly. These fuels definitely have to go through these expensive protocols. These fuels, for example, to answer your question, palm, jatropha, soybean, beef tallow, biodiesel, were created in Susan Williams' laboratory, and then she runs a full ASTM test on it. And so then we make sure that all these fuels that when we test are within the specifications that ASTM wants for biodiesel. And so these are all certified fuels, 100% certified fuels, and then we test those. But it's a great question. We just can't test fuels nilly-willy. We have to make sure that they conform to the standards.
Just a curiosity question. You touched briefly on the hydrogen carbon dioxide assisted biodiesel and biodiesel.
Yes.
Have you ever tried just hydrogen assisted? I mean, what's your kind of opinion on that? Is that something that works well for reducing fuel economy, just hydrogen by itself?
I love hydrogen. Hydrogen is the perfect fuel for internal combustion engines. This paper, what we actually did in this paper, this is a master's work, one of my students. He went through and reviewed the hydrogen-assisted literature, and we documented all of that information. It's almost a review paper in itself. Hydrogen has got a laminar flame speed. If you look at gasoline, the laminar flame speed is around 40 or something like that. The laminar flame speed for hydrogen is 191. It's an extremely fast-burning fuel. What this allows us to do, and we found through this experiment, is that when we add hydrogen, our thermal efficiency goes up. So we get better fuel economy. I love hydrogen. I would burn it all day long. The problem is we don't have a hydrogen infrastructure.
Yeah.
But if you had a fuel reformer, and let's say you had a glycerin tank and you're able to reform and put it into a tank of hydrogen on board your vehicle, we could use that very much to augment fuel production. I love hydrogen.
Can I ask your opinion follow quick? I know a guy who has he had a big diesel truck, and he put an electrolyzer on his truck. So he essentially put a big water tank in, put an electrolyzer in, and then ran that off and then essentially used the electricity to run that off the generator and then put the hydrogen fuel. And he was claiming like 20 to 30%, better fuel economy doing that. And I was a little skeptical. I'm just curious to see if you think that's feasible, unfeasible, or? It's
unfeasible. The electricity it takes to create the hydrogen to augment the boost you get is more energy than actually what you're going to get.
That's kind of what I thought maybe he was driving a little easier.
The first law and second law balances do not work out on that. You might see reduced fuel consumption a bit, but overall, where's that energy coming from? From your alternator.
Yeah.
So you're pulling that off the engine. The balance does not work out. If I had a tank of hydrogen, though, if I could fill up with a tank of hydrogen, bam, stick it in, put it in the intake, good to go. Yep. Yes. Go ahead.
Okay. So you mentioned the heat exchangers, adding those to a car to improve the efficiency.
Yes.
And you said that that had been done in the 70s.
Yes.
Could you elaborate on what was done and why they took it out? Is it just too expensive, or is it car too heavy, or would they prefer lower efficiency?
The question is basically, why did they do it in the past and then not go through with it? fuel cost, because when they were implementing it, the fuel prices were spiking, and it made a lot of sense. And if you looked at the cost return on it, it was a couple years, 2-3 years. You do have to consider packaging constraints, so you do have to play that role. But when fuel prices dropped in the 80s, the cost return on it, the economics did not make sense. And to add that additional packaging on top of that and the additional weight, the industry moved away from it. But now what's happening, our fuel prices are much higher, so that the economics is more beneficial, and we have better technology on the heat exchanger side. So not only do our payback went from this long, be taking into account fuel costs is here, and then better technology now is here. So in 5-10 years, you will see cars with this on, without a doubt. 10 years, you can come back and tell me I'm wrong, but we will see that because it makes practical sense. And that's why I wanted a student work in this area. No one has thought of this, though. This is our own. We have a paper that we're submitting to SAE that we're really hopeful about, see what it says. Could be a great idea, could be a horrible idea, but it's an idea, right? That's what we're trying to do as researchers.
Yeah, you mentioned product from Centrolium is being tested by you.
Yes.
I was under the impression that Centrolium was out of business, and
we got it from another partner who got it from Centrolium, and they might have just had it stored for a while.
Okay.
So maybe that was their leftover before they went out of business. But yeah, we know it's from Centrolium. I can't tell you how we got it. We know it's from Centrolium. I just called up someone one day and they said, "Yeah, we've got some stuff lying around. Here, we'll send it to you." We have the specifications with it and everything, so we know what's in there.
Yeah, I believe it's a Fischer-Tropsch product.
It is. It is a Fischer-Tropsch, I think, from natural gas, if I understand correctly. It was either biomass or natural gas. We didn't know the exact specifics on that, but we know it's a Fischer-Tropsch.
It was natural gas.
Question for the fuel injection.
Yes.
What kind of nozzle you use?
What time, I'm sorry, for the fuel injection, what type of, what do we use?
Spray nozzle. How do you do it?
Spray model?
Spray nozzle.
Oh, spray nozzle. Oh, for the fuel injection in here or for the reformer?
For your test. Do you use the same spray nozzle to test the different fuel?
Yeah.
And maybe I think the different fuels you need a different nozzle to test performance.
That brings up an interesting question. When we change fuel, should we be changing the engine hardware at the same time? Ideally, yes. Ideally, your engine is tailored to that specific fuel. The problem is, from a manufacturing standpoint, how can they manufacture if you don't know what your fuel is going to be? Right now, when I fill up on diesel, I drive a diesel car and practice what I preach. I'm probably filling up with 2% biodiesel, maybe 5% biodiesel. The properties will be different. Engine manufacturers don't know that, so they have to design a fuel injector for basically petroleum diesel. So I agree with you. Ideally, if we could develop a better biofuel, we could develop the engine to handle that better biofuel, and we get even better. Yes, that would be wonderful. I'd be happy to do that. Yes.
Thank you for the presentation. Very interesting. Just have a question. Right now, I mean, everybody knows that ethanol works. We put it every day in our cars.
Yes.
So I explain. Have you looked at the any other oxygenate, particularly butanol? The industry, chemical industry, is trying to sell butanol as a new trade.
Yes.
New ethanol, actually, because we've got more energy, similar to gasoline, but to what extent that is doable for an engine?
Butanol is definitely a viable fuel for engines. Unfortunately, our engine test cells are not set up to run a direct ethanol type of fuel, all type of fuel for spark ignition engines. We're running diesel engines, but I think it's almost like the Wild West. Is that I think there's a lot of different fuels out there that all have their own merits and benefits, but they also have their own drawbacks. All I do as a researcher is say, you give me the fuel and I'll give you what you want to know about it. So if you give me some butanol, I'm happy to test it with diesel, I'm happy to test it with biodiesel, I'm happy to test it as a mixture and see how it impacts the engine. And I can tell you specifically what's happening and how you have to change injection timing. I should say, not me, my students will be able to tell you all that. But yeah, I've heard a lot of great things about butanol as a potential product.
You do it with gasoline, not with diesel.
We can't run it in our engine with gasoline, unfortunately. The engine is just not tailored to that type of engine. The reason we chose diesel is, one, I drive a diesel, but that's not the reason. You know, the majority of trucks on the road, your commercial, your economics are tied to the trucking industry. All the big trucks use diesel engines. So your major fuel user is petroleum diesel. So that's why we chose diesel, because we felt like if we had to build one test cell, where could we go? And it's also very unbelievably difficult. We couldn't find any single-cylinder ethanol or gasoline type of engines. So we're limited to that area. But there are plenty of SAE papers where they're looking at ethanol and diesel, butanol and diesel. So it is a possibility.
Thank you so much.
Well, thank you for having me.